Hello everyone, my name is Bernd Schmölzer and today it's my pleasure to talk about gallium nitride in automotive. I am field application engineer for VisIC technologies in Europe. Gallium nitride is already standard in certain applications, like shown on the left side, namely chargers, audio amplifiers, meaning Class D amplifier, data center, power supplies, and solar inverters. And companies are making already advertisement with it, where the main arguments are efficiency, the reduced size, and the improved thermals. One question I will try to answer in this presentation is if these switches can also be used in automotive, like shown here on the right side, namely the onboard charger, motor inverter, and hopefully also in future the fuel cells. This slide shows three different technologies, where the first one is the MOSFET, second one is gallium nitride from VisIC, and the third one is the silicon carbide device, all at the same voltage class and all of them in the same RDS-on class, which is 650 volt and 22 milliohm, the typical value. And for these three devices, I calculated three different figure of merits, where the first one is multiplying the RDS-on with the K charge. The second one is also RDS-on with the reverse recovery charge. And the third one is RDS-on times output energy. The reference value is the MOSFET. As you can see here in the first row, we have the 100%. And now you can see for the first figure of merit, which is the hard switching figure of merit and showing the driving losses, VisIC is beating both technologies by far. Gallium nitride has only 22% from the MOSFET device and is also below the silicon carbide device. Here you see the formula how to calculate the power of these driving losses, and what is important to mention that this is depending on the switching frequency. The second column is showing then the hard commutation figure of merit, where it's clear that there is no reverse recovery charge for gallium nitride for VisIC technology, but you can also find gallium nitride cascode devices on the market, and for them this figure of merit or this zero reverse recovery charge is not valid, because they have one low voltage MOSFET in series they are using here. And this is the enabler for using topologies like the totem pole PFC. The hard switching figure of merits, which is important for motor drives, is considering the output energy, as you can see here again, dependency on the switching frequency. And surprisingly, silicon carbide is even above the MOSFET, and again, gallium nitride is beating the other two. So in all three figure of merits I've shown here, gallium nitride is the winner, and if this is the case, then I'm questioning myself why not everyone is buying gallium nitride, and let's try to answer this in the next slides. GaN structure defines reliability. What is meant with that? These standards are made for existing technologies, the Q101 or the JEDEC, like the IGBT, and are partially not sufficient for gallium nitride. The big picture on the right side shows the known lateral device buildup, where the 2D electron gas is between the GaN and the AlGaN layer. All GaN devices are by default normally on devices. The gate structure splits them then into a depletion mode or D mode and an enhancement mode or E mode device. The P gate GaN with the recessed gate reduces the AlGaN layer thickness, leading to a normally off device, which is at the same time its weakness in reliability because of leakage currents. Let's dive a little bit more into VisIC's D3 GaN technology. VisIC is using an insulated structure, like shown here on the gate, that prevents leakages, which otherwise may lead to defects and failures. We are using optimized field plates on the gate and on the source to prevent excessive E fields, especially again here near the gate. This leads to a shorter pitch and through that to a lower specific resistance. This combination results in a superior performance with very high reliability. How is the portfolio of VisIC looking like? We have discrete devices shown here with the 8 million device in a topset cooling package, leadless and fully isolated. Then we have the same package applied here on the 22 million. In the second generation, we will have a leaded package, which is further increasing the reliability. And we have a concept of 60 million. The bare dies are spanning from 18 down to 5 million. And to test all these devices, we build up some prototypes, like shown here, a 2 million half bridge with a current capability of 600 amps. And then we have some half bridge modules already in production, like here the 4 million with 300 amps and the 2.5 million with 400 amps. Why are the depletion mode devices from VisIC the right choice to be used in high voltage automotive applications? They are robust and they are optimized for automotive and for the high power applications. They are providing a better performance as shown in the figure of merits in the previous slide, and they are requiring a standard positive gate driving. You don't need to drive them like other devices with a buck boost or negative. The switching characteristic is determined only by the gallium nitride device and not by the MOSFET which is in series, which is the case for a cascode. They are easy to parallel, and this enables high current applications. The discrete devices, as shown before, are isolated and having a very low junction to heatsink thermal resistance. And for sure, all of them are cost-effective solutions, because in our case, the GaN is based on a silicon substrate. With this slide, I finish my presentation and say thank you very much.